Hello, Algebra 1 students. Welcome to Simplifying Radical Expressions 2. Moving on with our radical expressions. Today's accompaniment is going to be the Apple radio station for movie soundtracks, and I'm going to try to keep it instrumental based on a conversation we had today in second block. So let's get started here and jump in. I'm going to show you an alternate method for simplifying radicals that some of you might like. So let's do that first. Okay, so the other method that we have here, it has to do with prime factorization, has to do with breaking down the numbers, okay? I'm not going to share with you what we're listening to in the video, but I will put it in the liner notes, or not the liner notes, but the description of the video, what we're actually hearing. Okay, so look at this first one. We have the square root of 128. So we're going to take the number 128 and we're going to find out its prime factors. So we're going to break it all the way down and find out its prime factors. So 128 is 2 times 64. 64 is 2 times 32. 32 is 2 times 16. 16 is 2 times 8. 8 is 2 times 4, and 4 is 2 times 2. So that means we have how many 2's here? We have 1, 2, 3, 4, 5, 6, 7. 128 is 2 to the 7th power. 2 to the 7th power. So I can think of this as 2 times 2 times 2 times 2 times 2 times 2 times 2. 7 of them? Yup. And what I'm going to look for here is perfect squares. Perfect squares are double factors. So 2 2's at a time represents a perfect square. And for every pair of 2's that you see, 1 2 is going to come out. Because 2 times 2 is 4. And the square root of 4 is 2. And the square root of this 4 right here is also 2. And the square root of this 4 right here is also 2. And then there's a 2 left on the inside. So 8 root 2. And this is a great method for these larger values, these larger numbers, because it's hard to find the perfect square that you want to find here. And you may not have noticed, now of course, duh, we did it right here. 64 is a perfect square. But if you like this method better, you might want to use it. It's also good for a problem like this one, where we're breaking this down. So 8, we can break it down and make 32 into 8 times 4. Okay, putting it back together and breaking down that 32 into 8 times 4. All right, so we see a 4, which is a perfect square, and we can take the square root of that, and then we see a double factor. So this one actually, if I had my calculator do 8 times 32, great. But what if I wasn't allowed to use a calculator? Well, the square root of 8 times 8 is going to be 8. And then the square root of 4 is 2. So this one comes out to a value of 16. Okay, and then the last one. And again, I can break up that number, 700. And if I just wasn't seeing the fact that 700 is 7 times 100, those double factors really can help. And when you take out the numbers, so the square root of 2 times 2 is 2, and the square root of 5 times 5 is 5. When you take those out, you're going to multiply it by what was already out front. So 5 times 2 times 5 is 50. 50 root 7. Okay. So let's talk about the division property of square roots. All right, so just like we can take apart a product or put a product back together, you can also take apart a quotient. If A is greater than or equal to 0 and B is greater than 0, you can put A over B, the square root of A over B, you can put separately, square root of A over square root of B. So some of these are going to be easy. Look at their example. Square root of 36 over 49 is 6 over 7. Almost identical here. Square root of 64 over 49, square root of 64 over square root of 49, 8 over 7. Sometimes you'll have to simplify the fraction first, and that's what I want you to see here. Let's divide both of these numbers by 2. So dividing them both by 2. And also let's cancel out that x with one of the x's up top. So now I have the square root of 4x squared over 25. And I can break it apart and find the square root of 4x squared over the square root of 25. So that's 2x over 5. So that's not hard at all. All right. Moving on. to rationalizing the denominator. To rationalize the denominator, we're making the denominator a rational number. When the radicand, that's that number inside, in the denominator is not a perfect square, you may need to rationalize the denominator. To do this, you're going to multiply both the numerator and the denominator by the same radical expression. So here we have root 5 over root 3. And what you're going to do is you're going to pick a radical expression that's going to get the bottom of this fraction, the denominator of this fraction, to no longer be a radical. Well, what can you multiply by the square root of 3 that's going to get rid of the radical? But square root of 3. So most of the time, to rationalize the denominator, you're going to multiply by whatever that denominator's radical is, or at least the simplest form of it. Now, when you're multiplying radicals, remember, you can put those back together. So right now I have the square root of 3 times 3 on the bottom and the square root of 5 times 3 on the top, which is square root of 15 on the top and square root of 9 on the bottom. Now I can take the square root of 9. Oh, that's 3. So root 15 over 3 is the same thing as root 5 over root 3. Please note, this is not a 15 right here. It's a square root 15, so you cannot divide that 15 and that 3. That's square root of 15 over 3, not 15 over 3. Let's try a couple more. Okay, so for this first one, we're going to break it apart first. And then we'll simplify it by rationalizing the denominator. So, root 3 over root 7. And what would I multiply the numerator and denominator by? Hopefully somebody out there in video land said root 7 over root 7. And that rationalizes the denominator. What does that mean, rationalize the denominator? Well, it means turn the denominator into a rational number. Turn it into a rational number. And there, that one's done. Square root of 21 over 7. And again, it's not 21, it's a square root of 21, so you cannot divide that. You got to leave it as is. Okay? On this one, we got to simplify that denominator first. So hopefully we recognize that 8 is 4 times 2, and we can take the square root of 4. That's 2. So now I have 2 root 2n in the denominator and root 7 in the numerator. In order to get that denominator to be rational, I'm going to multiply by that radical on the top and the bottom. Now, when you have an expression, you're not just allowed to multiply by anything. You have to multiply by a value that is equal to 1. Let's think about how this is equal to 1. It's a value over itself. A value over itself. And that makes the value of this whole fraction is really a 1. And multiplying by 1 is fine. Multiplying by 1 is your identity property. So multiply the insides of the radicals there, and you get 14n for the numerator. And in the denominator, we have 2 times. Now the square root of 2n times the square root of 2n, here's a great shortcut. Anytime you multiply a radical by itself, you just get the radicand. So that's 2 times 2, notice it's 2 times 2n, which is 4n. And again, that problem is done. It looks awkward, but it is finished. And if you think back to your previous video, 1, there's no perfect square factors in those radicals, or in that radical. There's no radical in the denominator, and there's no fractions in the radical. And those were those 3 rules that we had when we were simplifying radicals in the first video. All right. Let's move on to something called cube roots. What exactly is a cube root? Well, a cube root is not this, but this is kind of cool. This is the root of a tree that grew into a cubic shape because of a grating that was over top of it, and I think that's pretty cool in terms of nature. But no, not that cube root. These cube roots. A perfect cube, first of all, is a number that's obtained by raising an integer to the 3rd power. So we'll talk about the first 6 perfect cubes in just a second, but it's raising a number to the 3rd power. In other words, cubing it. To take the cube root of a number, you're going to find the perfect cube factors, just like we found the perfect square factors when we're taking square roots, and we're going to simplify. This is the symbol that is called a cube root. This number out here can change. That's called an index. And for cube roots, it's a 3. In a square root, it's kind of like that number there is a 2, but it's invisible. We don't see it there. We just know it's a 2. The first 6 perfect cubes. Okay, well, what would they be? 1 cubed, which is 1. 2 cubed, which is 8. 2 times 2 times 2. So 2 times 2, 4 times 2, 8. 3 cubed, 3 times 3 times 3 is 27. 4 cubed, 4 times 4 times 4 is 64. 5 cubed, 5 times 5 times 5, 125. And the last one I want you to know, a little bit out of space here, 3 cubed is 216. 36 times 3. Times 6. So 6 times 6 times 6. 6 times 6, 36. Times 6, 216. And, I should probably double check that real quick, just to make sure I'm not messing up, considering my screw-ups in previous videos here. 216. All right, let's simplify a couple. 3, in fact. So we're going to start by finding our perfect cubes that go into 16. So based on the very short list we just had, what is the perfect cube that's a factor of 16? Well, based on that list, it's 8. So instead of a perfect square, it's a perfect cube. And this is how I can use that method from earlier. Okay, I can think of this if I prime factorize all the way down. Oop, not 3. Fix that. 2. 2 times 2 times 2 times 2. Instead of looking for double factors, you're looking for triple factors. That's the same thing as this 8. Now, I can take the cube root of 8, or of 2 times 2 times 2. The cube root of 8 is 2. And then I still have a 2 left on the inside. How about this one? Can you think of a perfect cube that goes into 81? It's 27. 27 times 3. So this one's going to be 3 times the cube root of 3. Because the cube root of 27 is 3, and then you got a 3 left inside. But you might not be able to simplify all of them. Let's write this one out by prime factorizing it. So the number 100 is 2 times 50. 50 is 2 times 25. And 25 is 5 times 5. Well, that's 2 times 2 times 5 times 5. No triple factors. So in this problem, it cannot be simplified. Simplified. There we go. Well, I hope you enjoyed our roots video, our radicals video number 2. And I think, guys, with that, we are actually done with everything we have to learn for the SOL test. So why don't you give yourselves a quick pat on the back? Pat on the back. And I will see you in class.